We shall see the frequency response of CS amplifier using LTspice. We shall have the first slide where we are assuming the CS amplifier, the MOSFET parameters as kappa, that is mu and Cx as 200 microampere per volt square. The VTO is 0.4, lambda we are assuming it as 0. So let us assume a threshold voltage of 0.4 and overdrive voltage of 200 millivolt. So assuming an ID of 1 milliampere, so we want to design an amplifier for a gain of 10. So we know that since VOV is 0.2 and VTO is 0.4, so we are supposed to have a VGS of 0.6 volts. So that's why for a VDD of 1.8, we are designing the value of R1 and R2. So it comes out to be 100K is the value of R2 and 200K happens to be the value of R1. The WBL can be found using the equation, so the current equation. So WBL comes out to be 250. So assuming the length as 1 micrometer, so width happens to be 250 micrometer, and we'll assume a source V in having a source impedance R source. And we are because we are doing the frequency response of a CS amplifier, let us also include two more model parameters, that is CGS1, CGDO. You can clearly observe here the CGS4, CGDO in the LTspice are defined per unit distance or per unit meter. So it is specified in terms of 100 nanofarad per meter, and CGDO is also considered as 100 nanofarad per meter. The actual value of CGDO and CGSO in terms of farad can be obtained by multiplying this farad per meter multiplied by the width of the transistor. So CGSO in terms of farad is nothing but CGSO, which is farad per meter multiplied by the width of the transistor. So in this case it happens to be 25 picofarad. Similarly CGDO is also 25 picofarad. So GM happens to be given by the equation and root of 2ID mu and Cox into WBL. Substituting the values, we'll get it as 0.01 ohm inverse. So we know the expression for the voltage gain in the midband is given by GM into RD, which is comes out to be minus 10 volt per volt. So magnitude will be 10. So let us look at the equivalent circuit of the CS amplifier considering all the capacitances. Now the equivalent circuit, as you can see, we are representing R in, which is R1 parallel R2. C in is nothing but CGSO plus C1. So CGSO is the value of the capacitance, and C1 is nothing but CGDO into 1 plus AV. So the overall C in comes out to be 300 picofarad, and C2 comes out to be CGDO into 1 plus 1 over AB, so which is now 27.5 picofarad. The R source we are assuming it as 1 kilo ohm. The value of RD is 1 kilo ohm again, and the coupling capacitor we are assuming it as 0.1 microfarad. So having all these values, we can actually find out the frequency response of the CS amplifier. This is how it is looking like. So this is the gain, which is in terms of dB plotted as a function of frequency. Now we have the expression for frequency f1 given by 1 over 2 pi Rin into Cc. For the values that we have seen the previous slide, the value of f1 comes out to be 23.87 hertz. Now this is having a cutoff frequency of almost 23 hertz, and corresponding to f2, we have a equation given by 1 over 2 pi R source into C in. So substituting those values of R source as 1k and C in as 300 picofarad, it comes out to be 530 kilohertz. So and similarly for F3, so we get the value of F3 as 6.09 megahertz. So with the values that what we have assumed, the cutoff frequency of F1 is 23 hertz, and this is 530 kilohertz. This is 9.09 megahertz. You can see now the bandwidth is f2 minus f1, so which is almost close to 530 kilohertz. Now since this is f2 is lesser than f3, so we consider f2 as a dominant pole, and this is the one which decides the bandwidth of the CS amplifier. So we'll just do this simulation in LTspice and come back to verify these values with the simulated values. We shall do the CS amplifier frequency response using LTspice. I can see we have rigged up the same circuit what was there shown in the previous slide. Now you can see R1 is 200k and R2 is 100k, which is providing a 0.6 volt at the gate, and this is RD which is necessary to get a gain of 10, and the W bell is modified to W is 250 micrometer and the length is 1 micrometer, which is giving a W bell of 250. And you can see there is a AC source. So because we are supposed to sweep the frequency, I cannot use V sign. The AC amplitude is given as 1. Now the question is why the AC amplitude is 1? Why not 0.1, something like that? Because whatever we are seeing at the output is just the output only, but when we actually see the output, we consider that output itself as a gain, because anything divided by 1 happens to be that gain. So that's why we are supposed to take the AC amplitude as 1 here. So by taking this AC amplitude as 1, and we are specifying the source impedance of that source as 1000 ohms here. So this is how we can specify the values. And let us first do the dot op and try to find out whether that 1 milliampere current is flowing, whether the MOSFET is in saturation or not. So let us do the dot op. So as you can see now, the drain voltage is at 0.8, so we are supposed to have minimum of 0.2. Now it is more than 0.2. Now the MOSFET is in saturation. Let us see the drain current. So drain current is also 0.01 amperes, which happens to be 1 milliampere. So everything is fine now. So we can certainly do the frequency response, for which we have to select this AC sweep. So we can know that okay, DC, the type of the sweep is decade, and the number of points per decade is 100. And well, let us start from a frequency of 1 hertz up to 100 megahertz. So we know that the cutoff frequency, the maximum cutoff frequency is 6 megahertz. So we shall just have this, and then I can see this is dot AC decade, 100 points per decade. It is starting frequency. This is 100 megahertz is the end frequency. So let me run this now. Now you can see we have the frequency response. So as you can see now, so we have a solid line which is representing the magnitude. This dotted line exactly represent the phase of the uh, output voltage. Now let us try to find out what is the midband gain. So we have designed the midband gain for a gain of 10. So in terms of dB, it has to be 20 log of 10. So 20 log of 10 happens to be 20 dBs. As you can see now, the frequency is almost 10 kilohertz. Now this is the cursor corresponding to 1. So you can see now the gain is 19.87, so which is very close to 20. So we are getting a midband gain of 20 dBs, which happens to be a ratio of 10 volt per volt. So let us find out what is the first cutoff frequency. So as you can see now, in the previous slide, we saw that the cutoff frequency happens to be this is our first cutoff frequency, which is at 23 hertz. So let us go back and see what is the frequency here. So let me minimize this slide, and let me just move one of the cursor, keeping the other cursor at the maximum. So please just have a look at this difference in the magnitude. So when this comes out to be 3 dB, the corresponding frequency of this cursor one happens to be the cutoff frequency. Please just have a look at this difference. So this difference should come out to be 3 dB. So 3 dB means okay, 3 dB down from the maximum corresponds to cutoff frequency. So now you can see it is 2.3, 2.4. Now it is 2.9. Now it's almost close to 3 now. Please just have a look at this is actually the cursor 1. The cursor 1 is the corresponding frequency of this is 23.45 hertz, and this is at the maximum. So this frequency corresponds to F1. So as we actually found in the previous uh, slide, you can see now this is the frequency F1 corresponding to 23.87. You can see that frequency is exactly 23.45 hertz. Now this way we can certainly verify the frequency, cutoff frequency of the first cutoff frequency of your CS amplifier. Let us have a look at the second cutoff frequency. So as we saw in the slide, so this is the second cutoff frequency, which is again 3 dB on the other side of the plot. So let me just move this onto the other side of the plot so that it is again 3 dB down from the maximum. So we are supposed to see this at 3 dB down. Just have a look at now, it is 2.9. So it is 2.9. Now you can see it's almost 3.09 dBs. See, the corresponding frequency is 510 kilohertz. Now this is at 9 kilohertz cursor. This is cursor 2, which is at 9.9 kilohertz. This is at midband. The other cursor, which is the cursor 1, it's at 510 kilohertz. Let us have a look at, okay, what was our theoretical f2 was 530 kilohertz. You can see it is very close to 530 kilohertz. Of course, 20 kilohertz difference in simulation in Semilog is very minimal, and of course we can see it is very close to 3 dB, and this cutoff frequency, which was 530 theoretically, is coming very close to 510 kilohertz in the simulation. Please just have a look at the third cutoff frequency, what we are looking at. Since third cutoff frequency is at a frequency of, so it is a bit difficult to make out where the third cutoff frequency is. So it comes out to be somewhere here, so which is at a frequency of around 6 kilohertz, sorry 6 megahertz, it is somewhere here. So which is a bit difficult to make out here because there is no much difference between, of course, if you want to clearly see the, you can see there is a change in the slope happening at frequency around somewhere here. So this corresponds to around 4 megahertz. Now, what is important in a CS amplifier is it is not all the cutoff frequencies. It is very much necessary to know the bandwidth of this. So what is the dominant frequency and what is the first lower cutoff frequency. So those two cutoff frequencies are exactly matching with our theoretical values. So this way we can certainly design a CS amplifier for desired bandwidth. So let us try to see the variation in the bandwidth. So as we change the value of source impedance. So let us go back to that slide and have a look at, so how do we how do we vary the value of RS and try to get different values of F2. Now you can see I'm changing the value of RS from, it's actually 1 kilo ohm, the value of RS for this particular simulation. That's why we got it as around 530 kilohertz. Let me change the resistance of R source from 1k to 100 ohm. Now I'm actually reducing it by 10 times. So this F2 will certainly increase by 10 times. Now 530 kilohertz will become 530 into 10, which happens to be 5.3 megahertz. Let me do the same thing now and try to see this F2, which was there at 530 kilohertz, will move to 5.3 megahertz. Let me just change the let us modify the value of RS and then come back and see the simulation. Now you can see I have modified the value of R series resistance from 1000 ohms to 100 ohms. So let me see the frequency response of this. Now since the value of RS has reduced by 10 times, the corresponding frequency of F2 should increase by 10 times. So let me have a look at the frequency of F2. So F2 happens to be at the higher end. So just have a look at the 3 dB point in terms of frequency. Now this is somewhere, now this is almost 3 dB, so it is 2.98. see the corresponding frequency. So the corresponding frequency is around 2.9 megahertz. So you may be surprised to see why it is not close to 5.3 megahertz. So why it is not close to 5.3 megahertz is because there is one more pole which is lying at 6 megahertz. In order to get this exactly at 5.3 megahertz, I have to keep the other frequency which was there at 6 megahertz too far away. When there is a when those two frequencies, when the F1 and F2 are very close, it is bit difficult to get exact cutoff frequency at this point. So let us move the value of RS to a lower value and try to see whether this 530 will become 53 or not. So let me just do. Just observe that I made the R series resistance happens to be just now 10 ohms. Now that F2 has moved too far away from F3 now. F3 is coming dominant. Now F3 actually found out to be 6 megahertz. Now we can see the cutoff frequency is almost 5.83 megahertz. Now this cutoff frequency is now purely due to the F3 now. So F3 is now dominant compared to F2. So this way we can see that dominant frequencies will change as the value of R changes.